A moving cart carrying a monkey at 80% of the speed of light passes by you. You're an observer standing still on Earth. Let's assume that there are firecrackers mounted on the ends of the cart, which can explode, and they're going to explode simultaneously in the monkey's reference frame. We'd like to know, in the monkey's frame, will he see the rear firecracker explosion before the front one? Will he see both explosions at the same time? Or will he see light from the front firecracker before light from the back firecracker? To answer this question, we need to draw the monkey's reference frame. So this brings us back to Galilean relativity. Galileo came way before Einstein, but even he realized that there were different perspectives for different people when it comes to physics and documenting the motion of objects. And so what Galilean relativity says is that there could be relative motion between the monkey and the observer on Earth. So in the monkey's frame, we want to draw the person moving to the left. At 80% of the speed of light. If we were to at the same time draw your frame, then things would look different. In your frame, you would be at rest, and the monkey would be moving. So whereas our cart could be located here at one time, it'll be moving forward at a high speed, so it could later be in a totally new position. In both cases, the speed is 0.8 c, but the objects are moving in opposite directions. And whereas the monkey would be located here at an earlier time, at a later time he can move to a new location. And so in your frame, he's the one that's moving. Now, one thing that makes Einstein's relativity different from Galilean relativity is that when we're doing this new type, we assume that light speed is going to be constant in all inertial reference frames. What does that mean? Well, it means that when the firecrackers explode at t equals 0, simultaneously for the monkey, they will send out light waves. And we can draw those crests that would be emitted. And they would head toward the monkey's eye at a speed of c, 3 times 10 to the 8th meters per second. And since the distances that the light has to travel to his eye are equal for both firecrackers, we should see that the crests will hit his eyes at the same time from both explosions. So this could be t equals 1, t equals 2, and then finally at t equals 3, it looks like he'll see both explosions. So the answer to A, the monkey is not moving in his own reference frame. So in his frame, light from both explosions will reach his eyes at the same time, because light travels at a constant speed. But now we want to analyze, when do you see the light from these firecrackers? First, let's analyze it from the monkey's frame. If we are to continue these wave crests, they would make concentric spheres around the dynamite as such. But you can see that one of them is going to hit your eye before the other. So down here we have t equals 1, 2, 3, and finally t equals 4. On the left side we have t equals 2, 3, and finally t equals 4. And so your head runs into the crest for the back firecracker before the crest from the front firecracker gets to you. So what we see then is that according to the monkey's frame, you see light from the back firecracker before you see light from the front one. And that's significant. The answer to B then is A. Light from the back of card explosion reaches you before you see the front explosion. Now, a person of mass cannot be accelerated to light speed. So you can't outrun light, is the idea. You're going to be traveling slower than those wave crests are. So eventually the wave crests are going to get to you, when we keep propagating that wave forward. Eventually it'll catch up to you. If it didn't, that would be a problem, according to Einstein. And so Einstein said that you can't outrun the speed of light. But now let's analyze the situation in your frame. If we're looking at things from your frame, and let's say we just have our monkey on a cart, and here's the dynamite. Intuition tells us that if two events are simultaneous in one frame, then they should be simultaneous in all frames. That's an assumption made in classical physics. Einstein questioned this assumption, and he came up with a reason why simultaneity is not absolute. In your frame, if the firecrackers go off simultaneously, then what should happen here? Well, if we draw a line from your eye to each firecracker at the time of explosion, and then let some waves propagate out from those explosions towards you, we see that the light from both explosions would hit your eyes at the same time. But this would be a contradiction to what had happened in the monkey's frame. You see, the monkey's frame shows that light from both explosions doesn't hit your eye at the same time. you see the one from the back of cart first. And so what Einstein said is what happens in the monkey's frame has to be consistent with what happens in your frame. In order for that to be the case, there's no way that those explosions could go off simultaneously in equal distance from your eye like that. So what Einstein said is, it must not be that they went off simultaneously. It must be that one of them went off before the other one. And so what he said is that the rear firecracker would go off first. The front firecracker here would go off last, so that the waves from the rear firecracker get to your eye before the waves from the front one. And so, for this question, in your reference frame, the rear firecracker has to go off first. Next question says, the proper length of a monkey's cart must be measured in the monkey's reference frame, and that's a frame where the cart is at rest. Let's assume the fireworks leave burn marks on the ground after exploding, and the firecrackers go off simultaneously in the monkey's frame. If you measure the distance between the burn marks, what will you find? Will the distance between the burn marks be larger than the proper length of the monkey's cart? Will the distance between those marks be equal to the proper length of the monkey's cart? Or will the distance between them be less than the proper length of the monkey's cart? We can give some numbers to our cart lengths. Since we're in the monkey's frame, when we label a length of a cart here, it can be called L sub 0, which is a proper length. Let's say the length of the cart is 100 meters. This is a proper length. Now, the fireworks explode simultaneously, and they're going to leave marks on the ground here. Now, when the monkey measures those marks in his frame, he's going to believe that the marks were made simultaneously, and therefore the distance between them is going to be the same as the length of his cart. So, if we measure that distance, I'm going to call it L of the marks. But is it a proper length or is it a contracted length? Well, the thing is, you have to realize that the marks and the ground are all moving. They're all moving to the left at a high speed of 0.8 c. And so this is not really a proper length that he's measuring for those marks. He's actually measuring a contracted length. And what would he measure it to be? 100 meters. Same as his cart. And so, does the person measure it to be 100 meters? The answer is no, because the person is not at rest in this frame. The person has their own frame. So what really happened in the person's frame? What happens is there's going to be an explosion in the back of the cart first. Because we said, according to Einstein's relativity, this explosion has to take place first. So it'll be like this. Later, the front one will go off. And they'll leave marks on the ground according to your perspective. But an interesting question is, what do you think about the distance between those marks? Does it really represent the length of the cart that made them, or no? And so, as you can see, the monkey's cart is moving. And if the back firecracker goes off first, the cart's going to move to a new position before the front firecracker even goes off. So when we measure the distance between those marks, it does not represent the length of the monkey's cart at all, would it? This would be called L of the marks with no prime, because this is a proper length. Between the burn marks. And is it 100 meters? It turns out it is not 100 meters. It would actually have the formula gamma times L prime so we have to find out what gamma is to find out how large that distance would be in the person's frame. Alright, so gamma for this situation would be 1 over square root of 1 minus v squared over c squared, where v is 0.8 c. Comes out to a gamma of 1.67. So now we can calculate how large the distance between burn marks will be according to the person. It'll be 1.67 times 100 meters, which is 167 meters. So that allows us to answer this question down here. If the fireworks leave burn marks on the ground after exploding, and they go off simultaneously in the monkey's frame, what would happen when we measure the distance between them? They will end up being actually larger than the proper length of the monkey's cart. Our burn mark distance was 167 meters. And the monkey's cart was actually only 100 meters. So there you go. Now it could also be interesting to find out how large the person believes the monkey's cart to be. Okay, so to do that, you'd have to take the proper length that you found here and then do a calculation on it involving gamma. Okay, so we would find that LO equals gamma times L prime for the monkey's cart. Okay, keep in mind that this is the cart now, not the marks. So we could do 100 meters equals 1.67 times L prime. And we get about 60 meters. Okay, so when the person is looking at the monkey's cart, person thinks it's only 60 meters long. And it's a 60-meter cart that's traveling to the right. It puts down one burn mark on the left here, and then at a later time puts down the second mark. And that's what accounts for this large distance between the markings. And so one of the things that Einstein showed that was revolutionary when it comes to our understanding of space and time is that he showed events which are simultaneous in one frame must not be simultaneous in an inertial frame that's moving relative to the first frame. Anytime you're observing an object move in your reference frame, the object's length is contracted relative to its proper length. And we also have the relativistic phenomenon of time dilation. Anytime an object is moving in a reference frame, then the time between events in that frame will be dilated or lengthened. So the final question is, if both you and the monkey are wearing watches, according to the monkey, what will happen? Will your watch run fast? Will your watch agree with the monkey's watch? Or will your watch run slow? Since you are moving in the monkey's frame, we're going to see the relativistic phenomenon of time dilation. And so it's going to take longer for your watch to tick in the monkey's frame. Therefore, your watch will run slow.